Now we want to derive the molecular orbitals for a square planar transition metal complex. So, as we've done before, our first job is to sketch out the situation. We have a square, and we've again drawn it in such a way as to make for the most convenient, accurate coordinates. So we notice that the z direction is this direction, and y goes this way, so we have a little schematic showing the orientation of our axes. The z-axis would be essentially coming perpendicular out of the board. So our S1 position, so this will be the sigma orbital on the first ligand, will have coordinates 1, 0, 0. For S2, since it's going in the y direction, it's going to have coordinates 0, 1, 0. For S3, the third of our ligands, it's going to have a coefficient of -1 because we're going one unit to the left, so it's -1, 0, 0. And last but not least, S4, the sigma orbital on the fourth ligand, is going to have the coordinates 0, -1, 0. So we haven't drawn it in this particular diagram. Keep in mind that when we use the correspondence theorem, in general, we're going to put the central atom at the origin. So it would have coordinates 0, 0, 0. In general, we don't derive the orbitals on the central atom. What we do is we work out the symmetry adapted linear combinations of the group orbitals. So that would be the S1, S2, S3, and S4 in this case. And then we manually look at which atomic orbitals on the central atom have the proper symmetry to combine with the symmetry adapted linear combinations. In the correspondence theorem, this is added by the fact that we can almost always immediately recognize which orbital we need by looking at the basis function for the particular irreducible representation that we used to generate the symmetry adapted linear combination. The first symmetry adapted linear combination that we are going to derive is going to use the A1G irreducible representation. If you look on the character table, you'll see that the first basis function that's listed is x squared plus y squared. So we notice right away that for each of these coordinates, whether it's a 1 or a -1, for the x or y coordinates, that whenever we square that, we automatically get a +1, and that we only have a non-zero value for one of the coordinates. So right away we could see that if we plug this x value into the basis function, we're going to get a coefficient of a +1 for S1. For S2, 1 squared is 1, so again the coefficient is a +1. For S3, the x coordinate is a -1, making x squared a +1. So therefore x squared plus y squared is going to again give us a coefficient of +1. So we're left with a coefficient of +1. That gives us our plus S3. Last but not least, our y coordinate here is -1. We plug it into the basis function to get a +1. The x value is 0, so 0 plus 1 is a +1. So we get our overall linear combination of atomic orbitals. Our set of group orbitals, in this case, is going to be 1/2 S1 plus S2 plus S3 plus S4. And the way we've drawn it here, since all the orbitals have exactly the same phase, we've drawn them in the same color. So we've used red here. And the orbital that has the proper symmetry to combine with the group orbitals is an s orbital. Typically it would be a 4s orbital if we're talking about the first transition row. And we can see that it has the proper symmetry to combine with the group orbitals. You may also have noticed that on certain character tables, listed with the A1G irreducible representation, is also a basis function of z squared. Now if we naively plug the z coordinates into the z squared basis function, we're going to get 0 plus 0 plus 0 plus 0. We get a function that has a value of 0 everywhere, which we often call a null function. When we're applying the correspondence theorem to deriving the symmetry-adapted linear combinations, at every step we want to reject the null function. So we're interested in the non-null functions. But we have a way to get around that by recognizing that z squared is just a shorthand for an orbital that's more accurately described as 2z squared minus x squared minus y squared. If we plug the coordinates into this particular function, we notice that for all of the sigma orbitals here, the coefficient ends up being a minus 1. So we could as well have written it up here as minus s1 minus s2 minus s3 minus s4. We could just as easily, in the process of normalization, multiply through by a minus 1 if we don't change the value of the function. It's a perfectly good solution for the Schrodinger equation. So what we end up with is exactly the same function that we had before. 1/2 s1 plus s2 plus s3 plus s4. We notice in our drawing that the symmetry-adapted linear combinations look exactly the same. They're all red because they all have exactly the same phase. The one slight difference, which may or may not be easy to see in this particular drawing, is that rather than having a simple 4s orbital, I tried to draw a slice through a dz squared orbital. So remember, dz squared kind of looks like a p orbital in a certain way. Looks like it has the two dumbbell lobes, but it also has the torus kind of donut around the center. So what I've drawn here is actually the torus part, the donut, the minus x squared minus y squared part. So we notice that's going to have the same phase as the symmetry adapted linear combination. So that orbital will also overlap and be symmetry allowed to combine with these particular group orbitals. The next combination that we're going to look at is the EU combination. So in this particular irreducible representation, we have a representation as doubly degenerate. That's what the E tells us. And we recognize, if we didn't know that already, by looking at the basis functions, we see x, comma y, both included in parentheses, tells us that there are two different basis functions, each of which gives us exactly the same energy. Last but not least, the U here tells us that we have an Ungerade function. By being Ungerade, in a certain sense it's an odd function. It means it's antisymmetric with respect to inversion. So if we go through the center, we get the same figure on the other side, but we've changed the phase. So let's do the combination for the x basis function first. So we notice that the coordinate for S1 is going to be the x coordinate, which is positive 1. For S2, the x coordinate is 0, so there's no S2 contribution. For S3, the x coefficient is a minus 1, therefore the coefficient of S3 is a minus 1. And last but not least, for S4, the x coordinate is 0, so therefore the coefficient is 0. We are left with, for the first of the EU combinations, S1 minus S3 with a normalization constant of 1 over the square root of 2. And we've drawn this particular function here. So we see blue for S1 and red for S3 because they have opposite phases. And the orbital that has the proper symmetry to combine with this symmetry adapted linear combination is a 4px orbital on the central transition metal element. For the second member of the EU irreducible representation, we use the y basis function. So for S1, the y coefficient is 0, the coordinate, so therefore the coefficient is 0. For S2, the coordinate is a positive 1, therefore the coefficient is going to be a positive 1. For S3, the y coordinate is 0, so the y coefficient is 0. Last but not least, for S4, the y coordinate is a minus 1, So the y coefficient is a -1, and we get S2 minus S4 with a normalization constant of 1 over the square root of 2 in front. So we notice that S2 and S4 have opposite signs, so therefore they're opposite phases. And the orbital that has the proper symmetry to interact with this combination is going to be the 4py orbital, if we're talking about the first transition row. So we see here's a case where for the EU combination, the x and y basis functions give us two orbitals that we would pretty much be able to recognize immediately were degenerate. The only difference between the two orbitals is that they seem to be oriented differently in space. Sometimes that will be true. In other cases, if you're familiar with the cases for either D3H or C3V, we end up with doubly degenerate combinations that you might not immediately recognize as being degenerate because the orbitals look fundamentally different. Last but not least, we're going to look at the B1G combination. For B1G, the basis function is x squared minus y squared. So one thing we can notice right away is whether the x coordinate is a +1 or -1, when we square it's going to be positive. No matter what for the y coordinate, whether it's +1 or -1, when we square it it's going to be a positive 1, but then the -1 in front is going to make it a -1. So, kind of fast forward through this, we can see right away by using the x or y coordinates from S1, S2, S3, and S4 that we end up with a function S1 minus S2 plus S3 minus S4. So S1 and S3 have one phase, S2 and S4 have the opposite phase, and the orbital on the central atom that has the proper symmetry to interact with this symmetry adapted linear combination of sigma orbitals is going to be the dx squared minus y squared orbital. Here we have models of the four symmetry adapted linear combinations, the molecular orbitals that we had just derived for the square planar complex, which has the symmetry D4H. At the left, here we have the A1G combination. So we notice that we have S1 plus S2 plus S3 plus S4, and that the proper orbital on the central atom that has the proper symmetry is going to be 4s or a 4z squared orbital. And we can see if we break open the model has a mirror plane going through the plane of the complex. In the center, we have the two members of the EU combination. So for the first combination, this is the x basis function. This is the y basis function. For the x basis function, we see our S1 minus S3, and we see that the orbital on the central atom that has the proper symmetry to combine with that combination is going to be the 4px orbital on the central metal atom. For this combination, this is the EU corresponding to the y basis function. So this is S2 minus S4, and we see that the orbital that has the proper symmetry is going to be the 4py orbital on the central atom. Last but not least, we have the high energy B1G combination. In this particular combination, we have the S1 minus S2 plus S3 minus S4, and the orbital on the central atom that has the proper symmetry to combine with all four of those orbitals is going to be the dx squared minus y squared orbital on the central metal atom.